Welcome! This is a recorded version of a talk that I gave recently at the MODELS'17 conference in thanks for the fact that they had decided that a paper that I presented at the MODELS'07 conference had turned out to be the most influential paper from that conference 10 years ago. I'm going to give it pretty much the way I gave it at the conference, but perhaps a little more slowly. You may be able to hear that I have a cold, but I'm going to do this now anyway so that I don't forget what I said. So here's the plan for my talk. I'm going to first of all say thank you very much for this honour. I'm deeply touched and of course happy that it turns out that my work was influential. I'm going to tell you a bit about that 2007 paper and about what's happened since, and just a tiny bit about related work that's still ongoing. And finally I'll say a little bit about why I think that paper seems to have been influential. So looking back to 2007, I had been working on UML and on software design and modelling for a while. So my background is that I was initially a mathematician, then I went into industry, and that was where I got interested in modelling and object-oriented design. I came back into academia, and about 10 years earlier than 2007, I wrote the first student textbook on UML. It's called Using UML. What I was interested in then, and still now, is the issues that arise when we try to separate concerns in software design, which is something that we do so that mere mortals can contribute to software design, and we are all mere mortals when we are focusing on other concerns, on the areas of expertise besides software design. So what I feel is that there's a huge amount of work out there which helps people to solve software design problems and verification problems, provided that they're very clever people who are prepared to devote their whole expertise to it. And that's great work, and I'm glad it's happening. But I'm more interested in how we can make software design easy. So at that time, the Object Management Group's Queries, Views and Transformations standard was new, and it was fairly poorly understood. But at the same time, the concepts of bidirectionality were around in the programming language field in particular. So I had recently been talking to Benjamin Pierce about his and his group's work on asymmetric lenses. So the idea of the 2007 paper was to bring together those concerns and look carefully at the QVT-R language from a bidirectional stat viewpoint. And it was followed up by that journal paper in SOSIM, Bidirectional Model Transformations in QVT, Semantic Issues and Open Questions, the same title as the conference paper. But if you're inclined to read this paper, I strongly suggest reading the journal version, not the conference version. Now the main point of this slide is to illustrate that I'm going to use this parchment style to indicate that this is a slide that I am reusing from the original 2007 talk. You'll be happy to hear that I'm not in fact going to give that whole talk again. So what do we mean by a model transformation? Well, classically speaking, a model transformation would be no more nor less than a function. It tells us, given a model in a set of models M, how to get a new model, little n, in a set of models n, and for purposes of this talk, set will suffice. Now, in this situation, if we modify our model M, say to M primed, how do we update the model from the n set? Well, we simply reapply our model transformation, our function, to getting a new n primed. The problem arises if we say we now want to modify the n model. Now the kind of situation you might have in mind is maybe M is a set of UML models and n is a set of generated code, and so people might work on both sides, modifying the model or alternatively modifying the code. And in either case, you might want to bring that pair of models back into a state where they're consistent. Going back and looking at the historical documents, the OMG's request for proposals for a language to express model transformations, and also looking at the very interesting, but although unfinished, document recording the requirements of some potential users of those languages referenced in the paper, It's very interesting, not least because what you see is that the requirement to be able to express bidirectional transformations was high up in the users list of requirements, and nevertheless it was only optional in the OMG's request for proposals. So why did it seem to be important to users? So this slide is rather of its time. I would draw it differently. If I were doing it today, I would probably use the UML model to Java code example. But in those days, we typically expressed this kind of thing in terms of the OMG's model-driven architecture concept, which had also recently appeared. So the idea here was that we might have an architecture team, say, working on a platform-independent model, and another team, maybe a product team, working on each of a number of platform-specific models. But the important thing to take out of this slide is that when you have to bring models back into consistency, it is quite difficult to do it via meetings between people for two reasons. One is, for the same reason that is the reason why we want to have multiple models in the first place, each team is familiar with their own model but not familiar with somebody else's model. And it may even happen that they don't even know the language in which somebody else's model is expressed, and therefore they will actually have considerable difficulty in reading somebody's model other than their own. And this is why it is desirable to have the recombination of the models, the redrawing of the models into consistency, done automatically rather than via meetings. Why might you need to do this kind of thing? Well, for example, if we've got a high-level product platform-independent model, the idea platonically is that you generate from that the platform-specific model, and then you do some work on that and fill in the detail, and then you generate from that the code, and then you do some work on that and you fill in the detail. But as anybody who's done software development actually knows, what will happen is that as the platform-specific model team fills in details, it will discover that some of the things in the platform-independent model were not quite right and should be changed. And at that point, you need to be able to loop back the way. So that was the kind of view that we typically had of such things in 2007. In 2017, we feel a bit more ambitious. We don't tend to think so much just about forward transformations with backward transformations being an afterthought, but rather we think about more thorough separation of concerns. So this picture now has to appear in all my talks, and the idea here is that we've got two groups of perhaps stakeholders who are going to be representing users of the system in different roles, and down here we have a different group of stakeholders. From the Greek letters you can assume that these are mathematicians, so perhaps these people are safety engineers who are determining and wanting to have satisfied the safety properties for the system. The coloured wires here are the bidirectional transformations. So the idea here is that each group of stakeholders makes the decisions that they have to make, the ones within their domain of expertise, using a model which records all and only the things that they have to be concerned with. And then these bidirectional transformations will take in these models, will read and write them, and will modify them as required to make them consistent so that they can generate running software out of those models. It's necessary to modify these models because not every collection of models independently developed by these domain experts will correspond to running software, so some changes will be necessary. So going back to the slide I used in 2007, our first idea about how to introduce bidirectionality might be to do the simplest possible thing, which is to say we've got a forward transformation taking a model M to a model N, and let's also now have a backward transformation taking a model N to a model M. Well, does that work? To explore why it doesn't always work, let's think philosophically for a moment about what actually needs to be done. So I've already talked in terms of consistency, that the job of a bidirectional transformation is to enable us to maintain consistency between models that may be being worked on in parallel. Perhaps it's UML model here, and perhaps it's code here, perhaps it's a platform-independent model here, and a platform-specific model here. That entails two jobs. We have to be able to specify a consistency relation, under what circumstances are a given pair of models actually already consistent and so that nothing needs to be done. And supposing something does need to be done, M or N have changed, I would say now, to introduce a slight subtlety, then how, out of the potentially many different possible steps you could take to bring one or both of them back into consistency, how should that actually be done? So the simple case is where once you've determined what consistency is, you've determined everything. So in that particular case, if there's a unique model N which is consistent with a given M and vice versa, then indeed giving a consistency relation T implicitly gives a forward and backward transformation, which are simply an inverse pair of bijective functions, as on the previous slide, and then everything is rosy. However, bijectivity is the exception rather than the rule. And I've given a couple of reasons here. What I would say now is rather, if your consistency relation is truly a bijection, then did you really need both kinds of models in the first place? Because what that says is that really your two sets of models are just two different ways of presenting the same information, which suggested that actually in the long run it might be better to train the two groups of stakeholders to work with the same model. Let's have a look at this now classic composers example to see the kind of thing we're thinking about. So the arrows here are representing a scenario that I'm going to talk through. This is not a commuting diagram. So what we've got here is on the left we've got two different model sets. So I've got an example here of a model drawn from a model set in which there are model elements representing composers, and each model element will include the name, the dates and the nationality of the composers, but there's no ordering between the composers. These are just two independent model elements, each representing a composer. On the right hand side, on the other hand, we don't have any dates. We still have names and nationalities, but we do have an order. In the right hand side model, Britain comes before Copeland in the order. Now the consistency relation that I'm going to draw between those model sets is simply that two models are going to be consistent if they record the same name-nationality pairs. So this model is consistent with this one because they both include Britain, who is British, and Copeland, who is American, and the dates on this side are irrelevant to the consistency relation, just as the order on this side is irrelevant to the consistency relation. Now, one thing you may want to do in this situation is to be able to generate a model on one side from a model on the other. And in order to do that, you have to explain how to create the information on the target side which is not present on the source side. So it doesn't matter precisely what this says, but the key thing that it's trying to do is to say, given that we have to invent an order, what order shall we invent? Once we have a model on the right-hand side, we can imagine that our user, our stakeholder on this side, who's interested in order but not interested in dates, is going to make an edit. So suppose that the user changes Britain's nationality to English and also adds a new composer, Sibelius. At this point we've got inconsistent models. This model on the left-hand side is no longer consistent with this model on the right-hand side, so what are we going to do about it? Now, drawing those back into consistency is going to involve creating new dates for the new composer Sibelius, and in this case we've decided that we're going to invent question mark dates in such a case. We discard the order, that's easy. One thing to note here is that it's important that we do not accidentally discard the dates that were present in the model up here. In other words, our user of the left-hand side model would be deeply unhappy if every time their model was brought back into consistency in the light of a change on the right-hand side, they lost the dates that they carefully looked up in their grove or what have you. So we have to take those dates from the model on the left wherever possible. So to bash that home again, the idea here is in general is that each side contains some information that's not contained in the other. And that means that we will have a genuine choice about how to resolve inconsistencies, and that choice may involve some computation. By the way, it does sometimes happen that one side does have all the information and the other side is simply an asymmetric view onto that side, and that gets us back to the view update problem as handled in asymmetric lenses. So a challenge that we have is how to express such bidirectional transformations. What would be a good language for expressing these things? So a person who knows what consistency is and how it should be restored needs in that language to have a powerful, flexible expression of ideas and good usable syntax in which to express their ideas there, and they need a sound underlying theory. Our language has to have semantics. Unlike perhaps in a language which is designed purely for communication between humans, a language which is intended to communicate to a computer about, for example, how it is to modify models, will have a semantics de facto. It'll be what the tool does, and so if we are not to get unpleasant surprises from the language, we had better have a semantics of the language so that we know what the tool does and so that different tools will do the same thing. So the QVT language, the language family, was OMG's initial attempt at a language to meet those requirements. So the language that we're concerned with is QVT-Relations up here. By the by, later on it turned out that this arrow, which is intended to represent a semantics preserving translation from the QVT-Relations to QVT-Core, is not actually semantics preserving, but that's by the by. So QVT-Relations, or QVT-Relational as I called it in those days, is a high-level declarative language, and the basic idea is that you write one text which simultaneously specifies the consistency relation that you want to hold between models, and also the transformations in each direction which should enforce the relation if it doesn't hold. In QVT-Relations, you always give it a direction and only one model will be modified. It doesn't allow you to specify a transformation which would involve modifying both of a pair of models in order to restore consistency. And there are some quite good pragmatic reasons for that, which I won't go into. It involves individual relations which you can think of as being something like spiders. You know, you say well, you've got a pattern which occurs in one model, and wherever you can find that pattern of elements in one model, there should be a corresponding pattern on the other side. And those kind of local specifications of consistency are combined to give a global notion of consistency via when and where clause. The OMG standard has a number of semantic issues, and this 2007 slide was quite politic about it. We say, understandably, the standard lacks precision in many ways. More interestingly, at that time, it lacks a clear set of requirements. It's not clear what you're supposed to be able to write in the languages, nor really what guarantees a conformant tool should provide. And I claimed in 2007 those issues were particularly acute for bidirectional transformations. At the time, we were only just beginning to investigate what properties bidirectional transformations ought to have. And here is an example of some of the issues that arose. The when and where clause characterization turned out to be really interesting, and I'll have a few words to say about that later. Reading the specification carefully and thinking about how to create a basic formal framework to capture it, we come up with the following. So let M and N be sets of models to be related, and then a transformation between M and N consists of these three things. We have a relation on pairs of models, and you read that as is consistent with. This lets us specify when M and N are consistent. And we have a function in each direction. And the key thing is that instead of our one argument functions of our early draft, in this case our consistency restoration functions each take a pair of models. So forward propagation says if I give you the current version of model M and the current version of model N, and they are maybe inconsistent, please, O transformation, give me a new version of the N model which will be consistent with the model M that I've given you. and correspondingly we can instead choose to modify the M model to restore consistency. And there are obvious engineering advantages to being able to specify all three in one text. That's not really the focus of the rest of this talk. In setting up that framework, we've already made some implicit assertions. The first one of which is that transformations are functions. In other words, they're deterministic. And I still strongly believe this, but not everyone agrees. So my view is that because in practice people will come to rely not only on what the semantics of a language insists that it should do, but what in practice the tool that implements that semantics does do, I think it won't be acceptable for different tools to interpret the same transformation text on the same models differently, or to do so differently on different days, and therefore I think from the very beginning our semantics should be deterministic in the sense that consistency restoration should be a function, as I just showed. We've already talked about the fact that transformations may need to look at both models, not just one, because otherwise we would be limited to bijective transformations. We'll need this, for example, in order to make sure that our transformation that was going to update the set of composers that includes dates didn't lose the dates for the old composers. And these assertions are justifiable for QVT-R given the specification, although there are pros and cons in both cases. Another assertion that wasn't really so noticeable at that point but has turned out to be important later is that the assumption here is that the models are all the information there is. There are no trace links, no delta information, and that again comes out of the QVT-R specification, but there are alternatives. Now I'm going to spend a few minutes looking at the properties that a bidirectional transformation ought to obey, and in this 2017 talk I'll only talk about the first two. By the way, the third one that I called undoability at that time is now known as history ignorance. So correctness just says that the transformation had better actually do its job. The idea of a forward consistency restoration function, T-forward, is to enforce the relation. T-forward on M and N is supposed to return us a modified version of N which is consistent with M, so it had better actually do that. When you test whether that new version of N is indeed consistent with the M that it was supposed to be consistent with, it better actually be consistent. Hippocraticness is clearly required by the QVT standard, which says that the QVT relations should have a check then enforce semantics. In other words, if a pair of models is already consistent, then the transformation should not change them. Turns out to be a little bit controversial in some quarters, because one of the things that this does is it says that if you ask a transformation to restore consistency on a pair of models which are already consistent, then it has to do literally nothing. It is not even allowed to do any kind of normalization or tidying up or reformatting. And again, I think that personally that's a reasonable thing to insist, and you can think, for example, about whether you will be happy to have your UML diagram completely relaid out by a transformation when you ask a transformation to bring it into consistency with a collection of Java code that it's already consistent with. But some people are not completely happy with this. So it's a choice that the language design can make. Here are some things that are talked about in the original paper that I'm not going to talk about here. Now I'm going to say a few words about what I did later on QVT-R. I've also done a bunch of other work on bidirectional transformations which is not specifically related with QVT-R, which I'm not so much going to talk about. So I thought a lot more about the when and where clauses that QVT-R uses to relate its basic relations and to build them up into giving a global specification of consistency from that rather local notion of consistency that the relations give. And the first thing I realised was that you can give a rather nice simple game theoretic semantics, restricted in the first place to the non-recursive case, in which you basically say that two models are going to be consistent if verifier has a winning strategy for a certain rather easy to define game, and that was quite fun. And then along with Julian Bradfield, who's an expert in the modal mu calculus, I was able to extend that to handle general when and where clauses with recursion, and then go on to handling the enforce mode of QVT-R, where we talk not only about whether models are consistent, but also about how we restore consistency when they're not. And the result of this is, I think, that we now have a good understanding of what when and where clauses mean, taking a rather French philosophical view that we should take the specification seriously as being all there is. But it also means we have a good understanding of why nobody succeeds in writing non-trivial things that really mean what they want, because there's a very tight connection between QVT-R's when and where clauses and the minimal and maximal fixed points of the modal mu calculus, which are notoriously difficult to use and understand, which I found very interesting. But the observation I have to make about this is that the cleverer these papers got, the fewer citations they got. Along the way, as I briefly mentioned before, I showed that QVT core is strictly less expressive than QVT-R, taking the direct semantics for each from the QVT-R specification, and hence the translation that the specification says preserves semantics actually cannot do so. As a result of all that, my conclusion personally was that bidirectional transformations I think are extremely important. I think they are going to be transformative for software engineering, but QVT-R is not the right language in which to work. It's not really a suitable language to take over the world industrially, and it's also not, in my view, a very good vehicle anymore for academic work on bidirectional transformations. So these days, here are just a few of the things that are ongoing in my own work at the moment. In the MODELS'17 conference, I have a paper about bidirectional transformations in the large, and there'll be a recording of that shortly. I'm interested in pushing the game angle. I think bisimulation and logic, this family of technologies that are very familiar in the concurrency field, are very promising for giving explanations of BX behavior in particular. So this is the idea that in order to have bidirectional transformations really fill the place that they need to fill in software development, we need to have good technologies and good tools for people to understand why they do what they do and debug them when necessary. And that, I think, is going to be a focus of my future work. And ultimately, I would like to be using the insight that we've gained from QVT-R to design a better language. So why was this paper influential? That's not the same question as why it should have been influential. Some things are clear. It was timely for the models community. QVT-R was new and people were having trouble understanding it. And at the same time, this paper made a link to other communities, especially the programming languages field, but also the graph transformation field and the database field. And therefore, for both of those reasons, it was followed up. So the BX community has been growing since. There was a Grace meeting in 2008, it was followed up by a Dargstuhl, and there's been an international series of BX workshops starting in 2012. And that URL there is for the BX wiki, where you'll be able to find a bunch of further information and, for example, a whole lot of examples. But perhaps the main thing was the paper was very easy to read. So thank you, and if there are any questions or comments or funding opportunities, I'd be very glad to hear from anybody.